Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. I will explain for the introduction for PBL. Okay. In terms of definition, SNR or signal to noise ratio is the ratio between the desired information or the power of a signal and the undesired signal or the power of the background noise. Also, SNR is a measurement parameter in use in the field of science and engineering that compare the level of the desired signal to the level of background noise. Okay, in other words, SNR is the ratio of signal power to the noise power, and its unit of expression is typically decibel dB. Also, a ratio greater than 0 dB or higher than 1 signifies more signal than noise. Okay, next I will explain for the fila table. Okay, for the facts. For the first fact, we analyze the resulting signal to noise ratio or SNR characteristic and propose a solution to reduce the noise impairment in the receiver system WP3. Okay, for the idea, using a limited bandwidth for learning issue, having a large receiver bandwidth allow for speedier data acquisition half the available bandwidth. Okay, for the second phase, resolve the noise impairment problem by proposing the best solution with the highest SNR level. Okay, for the ideas to get the signal to noise ratio, subtract the noise value from the signal strength value to find the quantifiable difference between the intended signal strength and the unwanted noise. For the learning issues, what are the equations to be used? Okay, for action, calculate the SNR by using its formula. Signal to noise power ratio S over N is the ratio of the signal power level to the noise power. Okay, mathematically S over N equal to PS over Pn. Okay, for the third fact is electronic noise. To reduce noise, use a filter. A lot in amplifier may extract a signal with a limited bandwidth and using the low noise amplifier. Okay, for the last fact, arrangement of the amplifier. Okay, for the ideas to achieve the lowest possible noise factor, and for the learning issues, the total noise factor that was created was the lowest. It is possible to achieve the highest signal, and the action is set up the amplifier such that the total noise factor is as low as possible. Okay, that's all from me. Thank you.
And now I will explain about this fishbone diagram for our group project. So our goal our output is to produce the highest signal to the noise ratio SNR output. So basically this is all the things that we need, or we can say the part that we need to achieve our goal here. So first is the material part, which is we have the amplifier and chamber. And for the measurement part, we have the gain and temperature value. And for the methods, we have the condition and limitation that we need to follow to calculate the result. And for the machine part, we have the RX antenna and cascade amplifier. And last part, we have the initial temperature and chamber description for environment. So we need this all of part to achieve our goal here. So basically every part plays an important role. That's all.
For the question for the PBL. So I'm going to find the solution for the question 1. So this figure 1 for the purpose of solution to produce the highest signal to noise ratio, which is SNR output of the communication system from consistent 5-volt reserve signal bandwidth of the 400 MHz. So from this is the initial temperature is 35 degrees Celsius, and this amplifier 1 is chamber 1, and amplifier 2 is chamber 2, amplifier 3 and chamber 3. So for the amplifier 1 is the 4 dB, and amplifier 2 is 5 dB, and for amplifier 3 is 20. So this device can be changed or relocated inside the chamber. So this value of the all chamber is chamber 1 is 77 degrees Celsius, and chamber 2 is 300 Kelvin, and chamber 3 is 450 Kelvin. So for the chamber 2, the range, the temperature is 25 degrees Celsius to 300 Kelvin. For the chamber 3 is 20 degrees Celsius to 450 Kelvin. So firstly for question 1, you can propose any practical solution based on following condition and limitation. So without change anything, I'm going to find the first calculation for SNR output. So this value for the temperature, initial pressure is the 308 Kelvin. For the bandwidth is 400 MHz, and for the SI, for the S input is 5 watt. So for the A1, we get the 2.512, and A2 3.162, and A3 is 20, and the chamber 1 350 Kelvin, and TE2 is 300 Kelvin, and for chamber 3 is 450 Kelvin. So for total TE, we get the with using this formula 5 to 6.08 Kelvin, with the T system is TE actually this plus TE plus TI, we get the 834.08. So to find input the noise power using this formula, noise power equal to KTB. So K is the value of constant 1.38 multiplied by 10 power of negative 23, and T is T system, and for the B is bandwidth 400 MHz. So noise power is the 4.604 multiplied 10 power of negative 12 watt. And find the output noise power. So firstly, we are going to find the total gain, which is we get the 158.859, and this noise power, total gain multiplied with the input noise power, we get the 7.311 multiplied 10 power of negative 10. So we are, after that, we can find the F by using this formula, 1 plus a T, TE divided a T. T is constant value is 290 Kelvin. So the F1 we get the 2.208, and the F2 2.034, and F3 is 2.552. Total F, we are using the formula, we get the 2.814, and the F system 1 plus in bracket FT minus 1 divide initial T close bracket and multiply T is the 280 Kelvin. So we get the 2.708. So the SNR input using this formula, SI is 5 and input noise is 4.604 multiplied 10 power of negative 12, we get the 1.086 power of 12. And for the SNR output, by using this formula, SNR input divide the F system, so we get the 4.01 multiplied 10 power of 11. So in dB is the 116.03 dB. However, we can increase, so that's all for the first calculation. But however, we can increase more SNR output by using the minimum temperature at limitation temperature at the chamber 2 and chamber 3. So we're gonna use the minimum of the range 25 and 22. And for And for the for the amplifier, we are going to rearrange it from the high to low. So from A3, which is a 20, to A2 and A1. So 20, 3.162 and 2.512. So this our new arrangement from A3, A2 and 1, and TE 350 Kelvin, and TE2 is 298 Kelvin, and 2E3 is 295 Kelvin. So we're gonna find the new total for TE. So our new total T is 369.56 Kelvin. This is more low than the first calculation, which is for first TE we get 526.08 Kelvin, and for the for the new TE is 369.56 Kelvin. So why is more lower? Because this formula. So first gain is more higher than the first calculation, which is A1. So that's why our temperature is more lower for TE. Because gain is indirectly proportional with the TE, so that's why we can load the temperature. And for the new T system, TE plus the TI 369.56 plus the 308, we get a 366.56 Kelvin. So this system also the more lower than the first calculation. It's about 200 Kelvin, I think, the difference. So find the new input noise power, and noise power is equal to KTB with the same value of K multiplied 677.56, which is a new T system, and bandwidth is same also 400 multiplied 10 power 6. So we get the new input noise power 3.74 multiplied the 10 power negative 12 watt. For the new output noise power, so gain is also same 158.859 for the total gain, and output noise power, and we get the 5.9541 multiplied 10 power of negative 10. So noise power is more lower than first question also, 7.311 for the first question, and while for the second is 4.941. And we're gonna find new F with the using formula F equal to 1 plus TAT divide T. So first F1 we get 2.207, and F2 is 2.028 and 2.017. So it's the same also for the first question. While this they are different, which is A3 is before this we will not use the A3, but for the new we gonna use A3 because the A3 is the first amplifier, and A2 is the second amplifier. Is A2 is remain same. So different is when we are gonna use A3. So we get the new F system is 2.2 for the new total F 2.2745 while the first question we get the 2.814. So the FT is more lower than the first calculation. So for the F system, our F system is 1 plus open bracket FT minus 1 divided initial T close bracket T. So we get the 2.2. So they're different for the calculation. So find new SNR input. So find our SNR input. The S input divided the N input, we got the 1.337 multiplied 10 power of 12. So we're going to use it for the find our new SNR output. So SNR output equal to SNR I divide the F system, and we get that 6.077 multiplied 10 power of 11 in dB is 117.84 dB. So the ratio of the low as an output for low is our first calculation, and for height height as our output is our new arrangement. So 4.10 for the first. Second, 6.077 multiplied by 10 of power 11 in dB, 116.03 dB, and for the higher is 117.84. So as we can see, volume of as an output is 6.007 multiplied by 10 power 11 or 117.84 dB.
So, today I will be presenting on question 2, which is without consideration the mentioned condition and limitation, what could you propose to further enhance the output SNR? So, my group has proposed 4 ways, which is the regenerative circuit, increasing signal strength, level shifting, and reducing noise. The first one is regenerative circuit, which also known as Q multiplier circuit. It is an amplifier circuit that employs positive feedback. It increases the amplification by applying back the output of the amplifying device to its input signal, and use active filter with positive feedback technique. The signal is amplified before being supplied back into the circuit. Thus, it gives two effects, which is reduce any noise and boosting weak signal. The second one is increasing signal strength. It is to minimize the noise effect. The signal is amplified before transmission. Thus, the signal is less vulnerable to attenuation and distortion. The third one is level shifting. The level shifting uses local shifter and frequency mixer to shift the signal to another frequency band by combining the original signal frequency with local oscillator frequency. Thus, it produces a signal that falls in the middle of the mixed frequency range. And lastly, reducing noise. From the SNR output formula, we can see that the noise is inversely proportional to SNR output. Thus, when SNR output is increasing, then the noise output will decrease. All measures are disturbed by noise include electronic noise and external events. The example of external events is gravitational magnet of the moon and temperature, while the internal electronic noise of the machine system can be reduced by low noise amplifiers. So that is all from me. Thank you.
Next, we go to the conclusion. For the conclusion, problem-based learning (PBL) is a student-centered approach in which students learn about the subject by working in groups to solve an open-ended problem. In terms of definition, SNR or signal-to-noise ratio is the ratio between the desired information or the power of a signal and the undesired signal or the power of background noise. Signal-to-noise ratio (SNR or SN) is a measure used in science and engineering that compares the level of a desired signal to the level of background noise. SNR is defined as the ratio of signal power to the noise power, often expressed in decibels. A ratio higher than 1/1 greater than 0 decibels indicates more signal than noise. This PBL activity involves group discussion on the wide-ranging of technical requirements to solve the noise impairment problems by proposing the best technical solution with the highest SNR level. By doing this problem-based learning, we learn a lot about on how to improve the signal and reduce the noise inside the system. At the end of this PBL activity, each group of students needs to submit a technical report and recorded video presentation of the proposed problem solution. So that's all from us. Thank you and Assalamualaikum.
Pikachu!